Good afternoon, students. Today we will be seeing the concept of cyclic codes, encoding and decoding. So, on the previous class, we have seen the concept of cyclic codes and the what are the is called error control coding. That we have block codes and convention codes. So, we have seen under the block codes we have handing code, PCS, cyclic, and RS codes, and conventional turbo code and threadless code. So, in your syllabus, we have cyclic codes and the conventional code, that is the threadless code. So, coming from the cyclic code, so it follows the cyclic redundancy CRC, and is one of the part of the linear block code. Okay, the code has been rotating in an anti-clockwise or clockwise. The MSB can be taken to LSB, or LSB can be taken to MSB. So LSB, MSB are the least significant bit and most significant bit. Okay, so for example, if you take this 1010, your MSB is your first one. This is your MSB. The last 0, this is your LSB. So coming on to the linear block codes, we have seen the properties of the linear block codes, and we have seen some of the examples how these properties correlate. And we have taken on a generator matrix, the purpose of generator matrix, and this we have proved it. Okay, the syndrome, whether under what condition there is an error and not error. The syndrome under we received the sequence into the parity check matrix. Okay, under the transpose of parity check matrix, if it is 0, there is no error. If it is not 0, there is a error. And the cyclic code introduction, we have seen the generation and detection type. Okay, systematic and non-systematic, we have generation type and detection, syndrome detection and syndrome calculation. So we have seen one example how the cyclic shift been occurring and the properties is being governed. And we have seen the concept of the polynomial representation, how message signal, how its generator, message generator and the code being represented in terms of polynomial. So from that generator, we have seen an example how this addition, multiplication, basic operation of polynomial, how this addition, multiplication and division being performed, right? So we have seen, we have taken an example of non-systematic multiplicative methods, and we have multiplicated and found the code word. And systematic division, we have seen this is the syndrome, the real syndrome remainder of M of P by G of P, and we have just added out, and we have found out the code word. Okay, code polynomial. So here you can see there is a correction, there is a detection been happening in the code, right? So here the generation part, we have seen the non-systematic methods of generation and systematic method with an example. Okay. So coming on from this previous slide, we are going to see the encoding and decoding of the cyclic codes. So let us take the generator polynomial g of n minus k of p of n minus k minus 1. This is a shifting property. Okay, this n minus k minus 1. So basically, this is a shifting property. So the code is going to be shifted out, or I can say this code is, you have a cyclic redundancy shift, right? CRC. So the code is going to be shifted. So by shifting, you can able to do some with the element like shift register or a flip flop. So either you can use shift register, or else you can use flip flop to do the operation. Okay. So here, property g of n minus k is not equal to 0, and g of g1 is not equal to 0. Let us see what this property makes. So we are going to converge the polynomial to a block representation. So let us take, there is an input here, k input bits. Okay, from that you will get the k bits. This is the message bits. Okay, next one you have a flip flop. F of is flip flop. Okay, or a shift registers. It's a memory element. So you have n number of flip flop. Okay, and intermediate you have g of n minus k minus 1, the first generator polynomial. Like you will have the second consecutively we will have the, I can see the generator polynomial equation, polynomial equation. From that equation you can able to define your generator polynomial. So in between you have g of n is there. And last one you have the switch where you will get the cyclic course. Cyclic course so this depends upon the memory elements as well as the generator polynomial. Okay. So let us take the g of p as pq plus p plus 1. So how let us take the generators 1 0 1 1. Okay, this is the message signal. Okay, so here you have to convert this to a polynomial. So converting to a polynomial, so how do you convert? So polynomial representation is like x cube plus x square plus x plus 1. Okay, what is 1 is nothing but x to the power 0. X to the power 0 is 1. Okay, so in this fashion you will be getting the polynomial which is available. P cube you have 1 here. Okay, p square is not available, so 0. So p is there 1. And last one is p power naught is 1. Last one will be having the real value 1. So you put it here. So it's 1 0 1 1 is equal to g. So likewise you can able to interchange from the polynomial to the code word message code word or to reverse of it. Okay, so okay, with the input message bit you have a flip flop, and then flip flop you are going to assign a generator form. So you have p cube. Okay, you have p cube, this line is there, and p square it is not available, so it's put in dash lines. So you will have the p, and last one you have 1. Okay, so here the in the detection process. Okay, so previously this nothing but how to represent in terms of block diagram. That's what is being given. Because in some problems, if they were given, give you a block diagram and try to find out the code word. So this is how it is being encoded. Next one is decoding. Okay, detection. How it detect. So you need to know some of the parameters like V of P is received polynomial, C of P is encoded polynomial, okay, and G of P is generated polynomial, and E of P is error pattern. So receive polynomial receives signal. Okay. C of P is encoded by the transmitter, which is on the transmission side. G of P is generated polynomial. This generated polynomial is mainly used to calculate the error. Okay, so you need to have a unknown generated polynomial function. E of P is the error pattern. So what's the output you got? So which bit has been you got an error. And next one is the how that error is going to be corrected. And B of P can be taken as C of P plus E of P. C of P is encoded polynomial and E of P is error pattern. Okay. How to correct it? So you have the syndrome here. Okay, S is taken as syndrome. REM is remainder. Remainder of E of P divided by G of P. Okay. If it is equal to 0, if the remainder is 0, no error. If the remainder is not equal to 0, there is error present. That's a simple thing. So remainder of V of P calculated as C of P and E of P divided by G of P. So if you take this remainder of C of P, G of P plus E of P plus separately, okay, this is going to be 0. Okay, C of P is going to be 0 anyhow because syndrome is mainly calculated on the receiver side. So C of P is lies on the transmitter side. Okay, so this data we doesn't want to know. So we want to know only the remainder of E of P by G of P. So that's the syndrome value. The remainder of E of P is this term is equal to 0. You have no error. If not equal to 0, error is present. Okay. So let us take the error patterns. Let us take 1 0 0 0 0 0. So let us take these error patterns available. Okay. And E of P is the error polynomial. Okay, or error pattern. So it's taken as we have 6. This is 1 x is not x1, x2, x3, x4, x5, x6. We have up to x6 of polynomial. So x6, x5, x4, x3, x2, x and 1. We have to convert this message. This is error message into a polynomial. Okay. And next one is the error pattern you have to find out. What is the error pattern? So error polynomial to error pattern you have to find. Okay. And how do you find it? You have to divide E of P by G of P, right? What is E of t x power 6 divided by g of p? G of p is already given here. T cube plus x cube plus x plus 1. Okay, you just convert this to x. Okay, g of x is x cube plus x plus 1. So you just substitute here in this function. So you have to do a modulo to division. Wonder that what happens. So x cube plus x of 10 into x is the this is got from this term. Okay, so you have to derive this x's, right? X to the power 6. So x cube multiply by x cube. Okay, x cube x is so x into x cube we have x power 4. 1 into x cube is x power 3. So now you do the modulo to add up. Modulo to add up. So you should have known this thing basically, modulo to adder and modulo to multiplication. Okay, so here 0 0 0 0 1 1 1 0 1 in addition and 1 1 0. The same bit will be resembles 0. Okay, if you take 1 1 it is 0. It is 0 0 is 1. Okay, so you have to know this. So you can see here x power 6 and x power 6 these are same, right? 0. So you write x power 4 x power 3. Similarly, you can put plus x. Okay, x power 4 you have x square plus x. This will be cancelled out. So similarly, you get the remainder as x square plus 1. So this is the error pattern. So you write right here x square plus 1 for the error of 100. For the column x power 6 you have error pattern x square plus 1. So if you convert to bit you will have 101. Okay, 101. So x square is 1 plus x is not available, so 0. Last digit is 1. Okay, put as 1. So similarly you can able to you can able to find out for the remaining terms. Okay, w divided by x cube plus 1 x plus 1 to x power 5 x power 4. Okay, so if you see, if you do the substitution you will get all these error patterns. So just convert to required bit. So this is the required bit you will convert. See is 1. How do you convert this to 1? X cube is 0, all is 0. Okay, and you have the last term only 1. Okay, so in this way you can able to find out the error pattern. So first question, g of b is equal to let us take generator polynomial as x cube plus x plus 1. Okay, and we will have the b is the received polynomial as 100 1000. Under the dimension under the dimension they given n comma k. This is already we see in our previous class 7 comma 4. This is n comma k. Okay, k is the number of bits, n is the number of digits. Okay, so n comma k, n is 7, k is 4. So under 7 comma 4 there is a constant generated polynomial function. You will see that in upcoming slide. It's already given as x cube plus x plus 1. This is constant, already been derived for the dimension 7 comma 4. And let us take this b into polynomial. Okay, so you have one x cube x not 0 1 2 3 4 5 6. So you have x power 6 as 1. You get it here. 5 is 0, 4 is 0, and 3 you have x power 3. Okay, remaining term log it won't come. So now what's the formula? E by g of p. Okay, so do that. So x cube plus x plus 1 division x power 6 plus x power 3. So we have only b, right? So you take that b. So already there is a syndrome calculation here. We have to just take this v here. Do the division. Okay, do the division. So at last you will get x square plus x. So it is not equal to 0. You have some function here. If you have here 0, then there is no error. But you don't have 0 here, right? It is x square plus x. So you should see this error pattern. Where is x square plus x? So it is lies on the x power 4. So the error may lie on this position. Okay, or else I can say that your third position from the left, this point, you have an error. Okay, and the e cap of p is equal to 4, and Let us find out the E cap of P. That is V of P plus E of P. Just add this V of P, okay, and E cap of P. This is error. So V of P is x power 6 plus x power 3, and E cap of P is x power 4. Just add it out. And the received error, what is the V is the received polynomial, right? This is received polynomial function exactly will have a code word of like this 101100. Okay. So if you see it has been altered here. You see the third bit here, it is 1, right? So there is a error present. Compare with this the given data. The given data is 0, okay, but the receive function, receive polynomial is you have third bit, you have error. Fine. In this way, you can able to find out the error. And next one, you can similarly you can have a set of question like they'll give C, then they'll give you E, and they will give you V of P. Okay, and G of same thing is 7, 4 dimension, and you just convert all those to polynomial. E code error and the received polynomial convert to the polynomial function, and you divide, okay, G of V of P by G of P. Okay, V of P is x power 4 plus x power 4 plus x square plus x. So how this came? So V of P is x power 6 plus uh, x power 4, okay, x plus 1 plus x power 6. So you need to add, okay, error function E of V of P. So when you add this, you will get it V of P of x power 4 plus x plus 1, where this x power 6 and x power 6 will be cancelled out. You have to do a modulo to addition. So x power 4 plus x plus 1 you get, just put it here, do the division, okay. So x cube plus x power 4, next one x square plus x. So same thing will be cancelled out, and you have to take the remaining terms, okay. So x square plus 1. So x square plus 1 you will be having, okay. So same thing, this is be saying 1 plus 1 will be cancelled out of this term, and the x square plus 1 will be getting, which is not equal to 0, okay. So you have some error. So C cap of P is nothing but is equal to x power close plus x plus 1 plus x power 6. Okay, what's the C cap of P? C cap of P, how can you find? So, okay, C cap of P is the addition of V of P plus E cap of P. Okay, you have to add V of P plus error function E cap of P. And you add, you get the code C cap of P, code polynomial. At the receiver. So you get x power 4 plus x plus 1 plus x power 6. Is the addition of V of P plus E cap of P. So what happens here? X plus this plus x plus 4 plus x plus 1. Just reshuffle. So 6, x plus 6, 1. You don't have x power 5, 0. X power 4, 1. X power 3 is 0. X power square is 0. And you have x, 1. Next last polynomial is 1, 1. Okay, what happens here? We compare with this C. Okay, compare with the C with this E cap of P. So the error is being detected and is being corrected. Okay, so there's an error, okay, and there's an error and it's been corrected. Okay, so when you add this corrected E cap of P, okay, error pattern, so the received signal code word has been corrected. You can see the given C and the given C, you have the error, and you have C cap of P, which is similar to the above given data 1010011. Use this here 1010011. This is exactly same. In this way, you can able to correct the error. Okay, so you need to know this modulo to addition and multiplication. Example of cyclic codes and generated polynomial. So here, what happens is G of P. G of P is the generated polynomial. We have to represent the P power Q, Q minus 1. That is G of Q, so suffix Q minus 1. That can be taken as N minus K. Okay. So what I say is like generated polynomial depends upon the cyclic code. Okay. That is N comma K term. You have to define how many N, what is the N value and what's the K value, message bits. Depending on that, your message polynomial differs. So if you take a Hamming, on the bottom you have Hamming code and PCH code. So under that, you can see the N and K value, right? N and K and the minimum Hamming distance RC. So with respect to NK 7, 4, 15, 11, and a different Hamming code, you can see the generator polynomials. Mostly you will get in exam N is 7, K is equal to 4. So since it comes under the since you're Hamming code, okay, in terms of Hamming code, you're going to see if in the problem they're given like minimum Hamming distance here, the N can K will be 7, 4. If they are going to deal with the BCH, mostly you'll get NS50 and 7S4. So for this 7, 4, okay, you have a G of P of 1, 0, 1, 1. Okay, that is exactly the PQ plus 0 plus P plus 1. That is we have seen on previous slide, XQ plus X plus 1. Okay, so the cyclic that is the cyclic code is generated by the multiplication. Okay, the X of P is a multiplication of the message and the polynomial. Or as you can say the cyclic codes. Okay, will be generated based on the message and the generated polynomial. So some problem they might have give the G of P. Okay, and some problem they won't give. They will give only the N and K as 7, 4, and you should have in your mind that for this commutation of N as 7, K as 4 as Hamming code, the G of P is PQ plus P plus 1 or SQ plus X plus 1. Naturally, you will get this generated polynomial. Advantage and disadvantage of cyclic code. So we have seen the cyclic code is a subclass of linear block code, and there are some advantages over non-block codes. Okay, non-cyclic block codes. Advantages is like error correction, error decoding methods of cyclic codes are simpler and easier to implement. Okay, you can able to directly implement in a flip-flop in a chip, able to transfer that code into a chip. Okay, so as well as the computation is very easy in the cyclic code, because instead of using a matrix, we go for polynomial representation. This method eliminates the storage needed for lookup table decoding. Okay, therefore the code becomes powerful and efficient. So there is a lookup table. Mostly the coders may look for some polynomial functions values. Okay, and the code J, for example, like generate a polynomial values. So in this case, we don't have to look for some lookup tables in the process of decoding. So, and it's become more powerful and efficient. The encoder and decoder for cyclic codes are simple compared to non-cyclic codes. Okay, and the cyclic code also detect error bursts that span over successive bursts. So there may be chance of bursting of errors may happen. The alteration may uh, the conversion of zeros or ones or ones to zero may happen to large successive message bits. For that's called burst error. So that can be detected. The cyclic codes will have well-defined mathematical structures. Okay, and we have efficient decoding schemes as available. In spite of this advantage, it also have some disadvantage, like error detection is a little simpler, but error correction is little complicated since the combinational logic circuit is error detector complex. You need to use, since the detector scheme, okay, you need to have a combinational logic circuit. Like we use some XOR gates, okay, XOR multiplication and adder to detect an error. So for this, the number of shift registers or the memory element can increase such a way that there is a complexity in the logic circuit. The generator, for example, let us take this one problem. Generator polynomial or 7, 4 cyclic code. They are given generator polynomial. Okay, as I already said, 7, 4. Sometimes they may give the G of T or they want to. So find all the code vectors or the code in non-systematic form. So we have seen the previous class systematic and non-systematic. Okay, so we go for non-systematic form. So let us take that n is 7, k is 4, and what's q? Q is n minus k. Okay, so n minus k is 3. So you have there will be total of 2 power k, that is k is 4, 16 message vectors of 7 bits each. There are some 7, okay, 7 bits, each 16 message vectors available. Consider vector as let us take a vector m, m3, m2, m1, m0. Okay, let's take this vector and let us take it as messages 0, 1, 0, 1. Okay, then the message polynomial will be you have to convert this to a polynomial function. Okay, so p square plus 1. Some books they will give us p, some book they may given as x. Both are both notation is okay. So and the given generated polynomial is this is the generated polynomial pq plus p plus 1. So you've taken one message bit and you have found out the polynomial and you have found out the g. As I already said, for non-systematic vector, the code can be represented as c or x can be represented as in term of m into message into generated polynomial. Just multiply it. So you have to do a polynomial multiplication, modular to multiplication term, that is p power 5 pq plus p square. Just do this one by one. Okay. So there you take the same term, do the modular add term. So once there is a pq, you have pq here, pq here. Okay. That is same thing will be negotiated to 0, right? According to modular to adder. So at last you will have p power 5 plus p square plus p plus 1. If you expand in terms of up to 6, okay, up to 6, we have 7 bits, right? So up to 6, you can message like starting from P0 to P1, P2, P3, P4, P5, P6. So you can represent this code in terms of this function as 0, 1, 0, 0, 1, depending upon this value. So the P power 6 is not available, so 0, P power 5 is 1, P power 4 is 0, P power 3 is 0, P power 2 is 1. Okay, that's the way you have to you can write the code vector. So the degree of our polynomial, the degree can be taken as n minus 1 is equal to 6. Okay, that is like how many degrees, how many degree you will get here. That is a degree. Okay, so you take n minus 1, okay, n is 7, 7 minus 1 is 6. You will have up to 6 degrees. So this is the code vector of the message vector 0, 1, 0, 1. Okay, for the one message we have followed the code vector. So this code vector is non-systematic cyclic code vector. So similarly, other code vectors can be used by the same procedure. Okay, that's what is given here on the next. So similarly, for different for 000 up to 111. Okay, 011011. Similarly, 100 up to like you can go up to 1111. What is code word? Adding back, you have to multiply the message into generated column. So this is the way the code word has been generated. To check whether the cyclic property is satisfied. So let us consider one x9. Okay, code word 101. That is 101100. That's this ninth one x9. Let us shift this code vector cyclically on the left by one bit position. Okay, so let us shift this 1 to on the LSB. So you get 0, 1, 1, 0, 0. Last one you will have 1. So from the observed table, this code word is nothing but it comes under 8. The previous code word 0, 1, 1, 0, 1, 0, 0, 0, 0, 1. Okay, the cyclic code word x9 shift provides the x8. So this can be verified with other code word also. So such a way you can able to find out the cyclic property is satisfied or not. That's already been seen on two properties, like linear property and the cyclic property. So this is been satisfied. It's a code word of another code. Okay. So another message it is a code word. So it has been available in some other message. So next problem is like systematic form. Similarly, same thing 7,4 g of p pq plus 1. Find all the code word for in systematic form. So the same thing, the same formula take this 0101 as a message signal convert to polynomial. Okay, you will have the p square plus 1 and this pq plus p which is generator polynomial. So to obtain the p per q, okay, we have to find out what is q. Q is n minus k, right? So n minus 4, you get 3. So p per q, m of p will be, so pq, m of p is a message signal. Okay, So here there is no like multiplicative messenger generator polynomial. You have to do this polynomial multiplication term like p power q m power p, m of p. So you get p power 5 plus q power 3. So the generator polynomial, okay, can take it as p power p plus 0 p square plus p plus 1. Okay, the next one to perform the division, the systematic form. Okay, you have to, because systematic form, you have to find out this formula, remainder of p cube of p or n minus q of m power p of m of message polynomial divided by the generator polynomial. For this, we have to compute it. Okay, so divide the message polynomial by the generator polynomial. So you will have a remainder here, p square. Okay, you get a it is not equal to 0. Okay, you get some polynomial here. So p square plus p are getting. So the remainder you are getting is p square plus p plus 0, and with the q is equal to 0, the equation can be written as c of p is equal to c square, that is p square plus c1 of p plus c0. Just want to multiply it. Okay, so thus c of 2 of p square, c1 p of p plus c0 is equal to p square plus 0 p plus 0. So from this equation, we can able to see that from the check bit, error check bit can be written as the form of 100. That's the c of p. Okay, so you can see here we have c as 1 here. Okay, since the p of you have a 0 here, right? You have 0 here. Next one you have a 0 from this polynomial function. So the remainder term of c of p can be taken as the 100. That's a bit. The code word is written in system form as x of m of k minus 1 in terms of polynomial. You can able to write in terms of messages to code. Okay, so x is the final code. So it is a combination of message and code. The code is a parity appended return bit. So 0101 is your already taken message. Okay, we have assumed it 0101. And the for the what is the code polynomial which you got is the 100. So this is a required cyclic code vector in systematic form. The other similarly the other code vectors, similarly what you have found out here, can be found out by using different message bits. Okay, so this is a systematic code where you have appended code word, okay, code bits on the right hand side. So M3, M2, M1, M0, and C2, C1, 0 are the code vectors in the systematic forms. So similarly, if you see on the backward, you have the non-systematic code words in terms of x power 6, x power 5, x power 4, okay, in terms of code vectors, which is based on the generator polynomial. But here there is a appending of the message bit and the code vector. Okay. So that's why you can able to solve basically the systematic and non-systematic cyclic codes. So similarly, this example too, if you see here, we'll say solve one problem related to that. So we have 7.4 code dimension. Each generated polynomial is given as x cube plus x plus 1, and the received sequence R. Okay, some book they will give R, some book they will give V. Okay, that's not a problem. So received sequence R is 100, 1000, and the sequence is whether find the sequence is valid or not. If not, correct it. Okay, so let us take the syndrome. Let us take the syndrome calculation. So S of x is equal to remainder of the ratio of V of x by G of x or R of x by G of x. Okay, this is the receives this one determines the receive sequence. Okay, so you have already given the receive sequence. So you have to convert that to a polynomial function. Okay, so you get it as x power 6 plus x power 3. How do you get it? I already told that this is x power 6, x power 4, x power 3, x power 2. Likewise, you have to find out which you have 1. Whenever you have 1, that can be taken as a polynomial. Okay, so you have x power 6 and x power 3. Remaining everything is 0. So your divide by g of x is already given x cube plus x plus 1. As I already says that this problem they are given x, some book they were given as p. Okay, that's not a problem. So divide it. Okay, you should make sure this first term is 0. So you have to do an multiplication with respect to that. Okay, and then do the modulo to addition. Modulo to addition. So this will be cancelled out. The similar 1 is here, right? Same thing, cancelled out. You have x power 4 plus this will be cancelled out. Okay, 0 x for addition. So next one, x power 1 we have x power 4, x plus x. Okay, this will be cancelled out. The remaining you have x square plus x as a remainder. So from this you can say that it is not equal to 0. So you have an error. This syndrome is not 0, so this is constrain the error. So it is necessary to correct the given sequence. Okay, this can be done by generating the error pattern. Okay, so for this you have to find the error pattern. From that we can able to solve the you can able to find the corrected message. So error pattern, since this is 6, right? So already I said that there are, you see the receipt pattern, you have the 6 bits. So you have to take the error pattern 6 with different possibilities. Okay, shift one to the right hand side. The possibility terms you have 1, 2, 3, 4, 5, 6 possibilities of error pattern. And the error polynomial, you just want to convert that bit to polynomial, and you have to find the syndrome polynomial, right? You have to do the multiplication. That is the convert everyone to a bit level. So now you can able to see the error pattern where it lies. So C of x is equal to the final C of x is equal to R of x plus E of x. Okay. R of plus E of x. You already see on the previous solved problem to analyze. We have seen this equation. Okay. So R can be R V of x plus E of x. So this is x power 6 plus x power 3, right? X power 6 plus x power. So where we have got it, we have already got this sequence, right? So put it here plus the E of x. So where is the sequence? We got CL. For this we got x power square plus x. That's the pattern, right? So where is x square plus x? So we are having, okay, at this junction. You see here, this is where you have x square plus x. This is the remainder which you got. So this is the our we can able to estimate that our error may lie on this bit position. It is x power 4. So you have to add that x power 4 here, that error pattern. So x power 6 plus x power 4 plus x power 2. So what happens is the corrected error coding pattern is 1, x power 5 is 0, x power 4 is 1, 3 is 1, x power 2 is 0, x power 1 is 0, and x power 0, you don't have any polynomial, so it's 0. Okay, so this is the corrected code word. Okay, so what is the receive R is 100 100. So here 100, that's in this position you have detected an error. Okay, so according to the question you have done it and you have detected and we have corrected it. So from there you can able to correct. Okay, so decoding cyclic codes. So here in this decoding of cyclic codes is lies on the transmitter side, sorry, on the receiver side. So mostly what happens is like on the receiver, the syndrome has to be done. Syndrome calculation has to be done. So it is a remainder of R of P for G of P or mod of that is a remainder of the modulator of R of P, which R is the message in G is the polynomial representation. Okay, or message that has been received. Okay, from the code board. So here this can be expressed also in terms of error pattern like E of P and the code word X of P. So R of P can be written as X of P plus E of P, or X of P is the code word and E of P is the error pattern. So we have already seen this decycling codes, okay, that is encoding and decoding. So this part lies on the decoding side, where you use the syndrome calculation for computation of the error bit. Okay, so the same similarity problem, one of the problem on the is given as 7 comma 4, okay, for different receiving code vectors 110 110, different three different code vector what you receive. So this is similarly exactly to the previous problem which you have seen. Okay, and as I already said, they already given this error function is 7 comma 4. So generator polynomial is sq plus x plus 1. So you have to divide it and you have to find out. Okay, so I'm skipping out because this is exactly similar to the previous one. Okay. So we today we have seen the concept of cyclic codes, the syndrome and non-syndrome with respect to some basic formulations. Okay, if you have any doubt, you can ask. And in this class, you will see the conventional code. So from that, we will be finishing up this unit. In this unit, they will ask problem based on systematic form or non-systematic form. Okay, and how do you correct from it? It's very easy, such a way that you have to divide your message in the polynomial generated polynomial, and you have to find out the error patterns. In which error pattern the error lies. Okay, and if you add those message and the if you add those the received pattern and the error pattern, okay, remainder of the error which you have got, okay, you substitute while dividing. If you add that, you get the received code vector. Okay, that is a corrected code vector. In which each position the code, in which bit position there is an alteration. You can compare with the received signal and the corrected signal. Okay, there will be alteration in any one of the bit position. So you can able to refer the book for this analysis, or you can approach this